Okay, please.
Okay. So hi everyone. Today I will present this paper, ULO-V4, Optimal Speed and Accuracy for Object Detection. So ULO is a model for object detection task. Let's first review what is object detection. As for the traditional image classification network, it can only do single object classification. For example, I fit in an image of a dog. Okay, it tells me there's a dog inside the image, but it doesn't give any position information. And also, if there are multiple objects inside, then the network cannot do its job. On the contrary, object detection can not only localize the objects, but it can detect multiple objects at the same time. And the objects can be from even different classes. In general, there are two types of detection network. The first type is called two-stage detector. This has been presented by Yizhe last time. The first stage is to propose a lot of regions of interest. So these regions are highly likely to contain the objects inside. The second stage is I'm going to crop the regions of interest and fit into the detection network. The detection network can give the final bounding boxes prediction plus the class probabilities. The disadvantages are obvious. So firstly, there are two parts for the network. So the two networks are usually trained separately in the original paper. So they're first going to train the region proposal network, then train the detection network, then go back to fine-tune the region proposal network, and so on and so forth. So they do it iteratively. The second disadvantage is that the detection network here only take the cropped feature map instead of this full feature map. So it kind of ignore the global context when making the prediction. So when making the prediction, I'm only looking at the pixels here inside these regions, and not the nearby pixels.
But the RPN model has already considered the global context, right?
Oh yes. So but here it's just ignore, yeah.
Yeah, so it means that the overall network, despite the fast RCN model, does not take the global context into consideration, but the overall fast RCN takes the global context into consideration.
Yeah. But that's what
for your first point, I believe that because we in a group we have discussed with Yizhe, so in detection framework, both RPN and the fast RCN model are trained jointly. Right. So anyways, so there is argument for this paper, or you bring this up?
This second argument is from the ULO paper. So the
ULO-V4 paper, right?
It's from the ULO paper, ULO-V1, yeah.
ULO-V1 paper, okay.
Yeah. They just claim this disadvantage of two-stage detector, but yeah, it's not necessarily true.
Yeah, please go on.
Okay. So that's why the one-stage detector was created. It is specifically designed to overcome these two disadvantages. So firstly, it integrates the region proposal network with detection network as a whole. So it is trained as a whole system, but we don't need to care. So the order of training. The second thing is that when I'm doing prediction, instead of cropping some regions, so here I'm cropping some regions and do the sparse prediction. In the one-stage detector, I'm going to make predictions at every pixels, so I will generate dense prediction. Okay.
Sorry, so here the backbone, so what's the difference between the backbone and the neck?
Oh, the backbone can be ResNet, VGGNet. The neck is the plugin modules they usually use to better extract the patterns. Yeah.
Okay, so it's for a different scale. It's just the pyramid scale.
Yeah.
Yeah, and for the dense prediction. So sorry, maybe I missed your point. How about the sparse prediction?
The sparse prediction is just for the two-stage detector. Remember the last step you need to crop. So you will have many sparse predictions. So maybe you don't have regions here, so you will not make prediction here. You're only going to make a small number of predictions. So it's called sparse. So here it is called dense because every pixel, it is connected to all the pixels in the last layer of feature map. So it is dense because there are many ways.
So this detector is more like, so the dense prediction is for both the dense and the sparse predictions for bounding box, right?
Yeah.
For bounding box, and the major difference is that the sparse prediction is more like a refinement of the dense prediction. So for example, the dense prediction reports a set of the bounding box, and the sparse predictions do the refinement and remove some part of the, am I correct?
But actually, if I'm using two-stage, then I don't have this dense prediction part. I just from here, then I directly have many regions, then I do the sparse prediction.
Yeah, I agree, yeah.
Then in one stage, I don't have the region of interest, this kind of definition. I just think every prediction is a region of interest.
Let me think about it. So in two-stage model, suppose there's a proposal predicted by the dense prediction.
No, there's no dense prediction.
No, I mean two-stage. I'm talking about two-stage model. For two-stage model, this is more like RPN, right? This is more like RPN, and this is more like the faster CN. Correct?
Oh yeah.
So now my question is, will be some proposal predicted by RPN model will be rejected by fast RCN model?
Rejected?
Yeah, for example, suppose the RPN model predicted a bounding box here, but so it will be feeding to the fast RCN model, right? But will fast RCN model reject this prediction?
I think so, because the fast RCN will predict the class probabilities.
Yeah, okay. So if it will propose a logo, but it is either belongs to, for example, logo and input box, it will be rejected. Okay, so it will be somehow called sparse.
Yeah, then maybe it has a class called background. So it has a class that is different from the rest of the classes there. Then if this get a large probability, then it will be rejected.
Okay. Okay, please go on.
Okay, so YOLO is a representative.
So let me bring it up. So if because in our paper we are saying that in classification model, if we're using the softmax or we're using softmax on the last layer, so do you remember that for the Siemens model we turn it into a high dimensional vector of 2048 dimensions, and we do not apply softmax on it. So is that possible that we apply a sigmoid for each output neuron? Is that possible?
So the effect is that each will be squeezed into 0 to 1.
Yeah, 0 to 1. So my point is that it certainly brings me to another point, that whether it is possible to using the classification model to perform the logo recognition in our Fishpedia work. So you can see we are using Siemens model, and we totally train the Siemens model in a classification way, right? So the only thing we do is that we remove the last layer. We just remove the last layers and to do the cosine similarity comparison. But it is also quite possible that if we train on the if all the logo, if the number of logo is fixed, we can design a network structure so that each output neuron will be feeding to an individual sigmoid. So one indicates true, false, 0 indicates false. So we pick the one with most prediction. And if all the neurons predict 0, so that means that given a brand or given a logo, it does not fall into any category of the brand.
But you have 2048 neurons.
Yeah. If all the neurons output 0, that means this logo does not belong to any of the brand.
But the number of brands is far less than 2048, so you need to.
Not necessary. Suppose giving a logo DBS has never appeared in a training set. By right, all the neurons can be 0. So that means this brand I have never seen it before.
Yes.
Yeah. Yeah. But the only problem is that this is a network design. So because I make argument in our paper submission, but I'm now thinking whether such argument is strong or not. Yeah, it just occurs to me, but no worry, let's go on.
Okay, so today I will just focus on YOLO family, which is one of the stage detector, one of the most famous. So the steps of YOLO is as follows. The first step is to divide the raw image into S by S grids. For example, we have a picture of 2 cars on the road, and we divide it into 3 by 3 grids. So here S is equal to 3. Then step 2 is to assign each cars to a grid. So we have 2 yellow grids, which are the responsible grids for 2 cars, and the rest of the grids are irrelevant. The third step is, because when we train the network, we need to create ground truth labels. So we need to create labels for each grid cell. The label is a vector of 5 plus n. The first element is called object name score. It specifies whether there is an object inside. So for responsible cell, it takes 1, and for irrelevant, it takes 0. The next 4 elements are the box coordinate, the ground truth box coordinate relative to the grid cell. So for example, for this car, Bx is just the center of it, the x coordinate for the center. I change the color. The x coordinate for the center of this box, and the y coordinates. Bw and Bh is the width and height. So once we know the 4 numbers, we know the exact location as well as the shape for the ground truth box. Okay? The next n elements are the one-hot encoding for class. So in this example, we only have car, but in real-life problems, we can have pedestrians, trees, streetlights, and so on, so different classes. Okay, so this is for the responsible cells. For irrelevant cell, I only have the first element, and note that so these are all question mark, because we don't create labels for these elements. There's no object inside this kind of grid at all, so we don't care. And they also do not involve in loss calculation. Okay. We know that the network is trying to learn Bx, By, Bw, and
Actually,
Bh.
I have a question.
Okay.
So how do you decide S?
S.
Yeah.
S you can choose.
But
so here I use
are you saying you are labeling all the images?
Let me reply these questions. So because you can see that, so when we do the predictions, we have a pyramid structure, right? So in journals, you can choose multiple S. So Ruofan, why don't you go to the previous slides?
Okay.
Yeah. So you can see, correct me if I'm not, if I'm wrong. So suppose this is a backbone, and this backbone will be output a net. Is a neck here. So the next, for example, here is maybe the S's will be maybe 7 or 9, and here S could be 11, and here S could be 26, something like that. So it will be output multiple S here. So for each input image, so it will be divided into multiple grid. So according to different scale. And each layer will be corresponding to different scale. For example, if S is equal to 7, it means it's going to detect large objects. And suppose S is equal to 26, it means that each grid is smaller. So it also means that it will going to detect as a smaller object. Okay. 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 May I make yourself understood?
Oh yes.
Okay. Please go on.
So when you have an input image, and because of the way you develop SELab, in the output feature map, each pixel will be corresponding to a recycle field, right? So this pixel will correspond to maybe a 7 by 7 recycle field. Then your S here is just 7. Okay. So the network is trying to learn these 4 numbers, bx, by, bw, and bh. But if we initialize these 4 numbers to be some random box, then it's actually hard for the network to converge because you will have different size of objects, and the networks are hard to learn all the object size. But suppose we have some prior knowledge. We know the approximate size of objects. Then we can actually design some fixed size boxes to start with. And these fixed size boxes are called anchor box. For each grid, I'm going to draw these anchors on it. And when I'm creating training labels, I'm not creating label for each grid. I'm actually creating labels for each anchor box. So here, suppose I have 2 anchor box of, I have 3. Suppose I have 3 anchor boxes. Then my label for each grid cell becomes a much larger vector. One notice that I only assign an object to 1 anchor box. So here only 1 anchor box get objectness score equal to 1, and the rest are all 0. Okay. So that's about the training labels. During prediction, the output prediction will be of shape S by S times 3 times 5 plus n. So you have 3 here because I have 3 anchor boxes, and 5 plus n is the prediction for the label vector. It's the prediction for objectness score, XYWH, and the predicted class probabilities. Okay. Then during inference time, there will be many predictions. So I need to design a post-processing way to remove the noisy ones. Step 1 is to do a score thresholding. So I only keep those boxes with high confidence score. The confidence score is equal to objectness times the classification probability. Okay, so once I apply this step, then I will left with only the important boxes. But here you can see there are many overlapping boxes, many duplicates. So I use the non-max suppression. So this has been introduced by Yizhe, so I just skip this. So you are left with only 1 box. Okay. So YOLO v4 is actually the 4th version of YOLO. There are mainly 2 contributions. The first contribution is that it summarizes the existing tricks in training object detection model. And secondly, it plays with different configuration and combinations of network structures. Let's look at the V4 structure. So the first step is I'm going to feed the input image into some backbone model. The backbone is just a SELab model, can be VGGNet, can be ResNet, can be anything. So here they use CSP.NET 53 is just they choose the best performing one. And the effect of backbone usually will shrink the feature maps while widening its channels. The idea is that each channel is responsible for detecting a different pattern, and this pattern can be represented by a feature map of much smaller size. Okay, so we then take the output feature map from the backbone and fit into max pooling with different kernel sizes. So here we use max pooling 5 by 5, max pooling 9 by 9, and max pooling 13 by 13. The idea of max pooling is to only take the most important information inside the kernel. So now we have 3 different kernel sizes. That means we're extracting important information at different level. For example, if we are taking the 5 by 5 kernel, then we are searching the most important pixel within a small neighborhood area. But when we are using 13 by 13 kernel, then we are searching inside a large neighborhood area. Okay, so the last step is to stack all together the feature map from max pooling as well as the original feature map. So this whole step is called spatial pyramid pooling. It's just trying to enrich the information we have. Okay.
So I will have a comment here. So the idea is compared to the traditional, the takeaway that compared to the traditional CNNs, it reflects the model in static model with different max poolings and with different stride. But anyway, so basically they're using the stride, but they're using the stride so that the final stacked feature maps will be of the same size.
Yeah.
Am I right? So,
yeah.
But this trick is that not like the traditional convolution layers, they're using these layers so they can capture multiple spatial relations about the images. So, okay, please go on.
So the next part is actually called path aggregation network. The layers are complicated, and I don't think it's necessary to understand every detail. But the basic idea is simple. It's just I want my network to be deep to capture more, to learn better. But when the network is deep, the information is actually lost when traveling through layers. So researchers just add some fancy skip connections to make sure the original information is well retained. So you can see there are skip connections here, skip connections here. Okay.
So, but anyway, so there's an operation there, right? So compared to the, so what does the, anyway, just like RESTnet, we will have additional connections for propagated learning effects back in a more effective way. But why we have such operations like the plus and the multiplications, and what these operations means, or what the benefits of this operation?
I think it's just some ways to improve the performance. Because here, if I just output these three feature map, then it's actually unfair for this feature map because it actually traveling further than this 2 feature map. So information will be largely lost when I reach this feature map. But now if I have this kind of skip connection, then my original information will be added. Something like that.
Please go on.
Okay. And the last part, so after this part is called path aggregation network. After the path aggregation network, 3 feature maps are output. You may ask why there are 3 outputs. You can see these 3 feature maps are of different sizes. A small one, a medium one, and a large one. So this one I have mentioned. one pixel actually corresponds to a receptive field in a raw image. So one pixel in small feature map corresponds to a large receptive field in input image. So small feature map can detect large objects, while large feature map can detect small objects. Okay. Then what does this output feature map look like? So this I also have covered. It's just of shape s by s times 3 times 5 plus n. Okay, this is the full picture. So that's all for the model architecture. Another key question when we introduce a model is the laws they use. Recall that there are two goals for object detection model. The first one is accurate localization. So I need a regression loss for x, y, and wh. The second goal is for accurate classification. So I need to have some kind of classification loss. The total loss is just can be decomposed into two parts, a regression loss and
sorry, Ruofan, I have a small question here. So YOLO V4 is a one-stage model, right?
Yes.
Okay, so it's a one-stage model, but it will be, it is actually extracted the details, features in a more, with a lot of more tricks.
Yeah.
Okay, including the multiple spatial, right? Is that the way? All the spatial pyramid pooling. Spatial pyramid poolings and the
path aggregation.
The path aggregation and the prediction head. So what is the novelty of the prediction head? So
it just borrowed from YOLO V3, so there's no novelty.
Okay, so the major difference is that it's going to, so basically the network, the backbone is deeper, right? Or it's deeper, or it just did the same, because as far as I remember, YOLO V3 still use .NET 53.
They use some kind of, this is called CSP.NET 53.
Oh, CSP.
Yeah. I think there's some tricks to save some computation, but the number of layers may be the same.
Okay, so as far as I learned, I think the major contributions or novelty lies in the spatial pyramid pooling.
Okay. But I think this.
So have you ever checked the evaluation? Sorry, I bring this up earlier. So
evaluation.
Yeah, the evaluation part. So they added so many tricks. So in terms of change the backbone, they apply the spatial pyramid pooling. They using the path aggregation network. So which one is makes the most fundamental or most significant contribution?
Spatial pyramid pooling.
You believe,
because the path aggregation network is already there.
Is it just like a, okay, so that's your belief that the major contribution like the spatial pyramid pooling, right? Or that's your belief, or that is what they claim?
That's what I believe, but correct me if I'm wrong. Yeah.
So do they have any report on the evaluation part?
Evaluation? I think I didn't look at the evaluation table because it's too long. Then.
Okay, I see.
But I just directly look at their code and try to draw their process here.
Okay, sure. Please go on.
Okay, regression loss and classification loss. For the regression loss, a natural option is to just use the normal MSE loss, which is the square difference between prediction and truth. But it kind of neglects the fact that X, Y, WH are actually close related because they form a box. So a better alternative is just to use intersection over union loss. It's just the ratio between the overlapping area between predicted box and ground truth box divided by the union area between predicted box and ground truth box.
So what do they apply? Is they using MSE or using IOU loss?
They use IOU.
Okay.
Yeah, and they use CIOU loss instead of traditional IOU. Okay. I don't put formula here, but there are two intuitions behind. The first intuition is that distance matters. The distance here is the distance between predicted box and the ground truth box. So here,
I see.
So
what does C means?
Oh, I don't know.
Okay. Please go now.
There are two cases shown as an example. So both of them have IO equal to 0. But obviously, case 1 is anyway better because it's closer to ground truth. The intuition 2 is the aspect ratio thing. So case 1 and case 2, their IOU are the same, but the shape of the case 1 looks better because it's similar to the ground truth. Okay. So CIOU is just a metric which combines this distance and aspect ratio information.
Aspect ratio is also the trick we play when we try to improve the false positive.
Yes. Okay. So as for the classification loss has two parts. The first one is the loss for the objective score. Predicting the objective score is actually equivalent to classifying whether there's an object or not. So it's just a traditional classification task, and we can use the traditional binary cross entropy loss. And so it's nothing new for the classification loss part. For the loss for the classification, it just uses the binary cross entropy loss summed over all classes. But my note is that for the box which does not contain object, then we don't care minimizing its classification loss. So strictly speaking, we only incur loss when the anchor box is responsible for an object. Okay, so here I add an identity function, which takes 1 if the object is present inside the box. Okay.
So it's based on the last one is just based on the lost object, right? So whether the box is responsible just based on output of the lost object, or the ground truth, or the
it's based on the ground truth. It's based on the ground.
Okay.
Okay. So ULV4 also introduced some tricks. The first type of trick they called it bag of free buys. I don't know why they gave it this name. It's just change of some training strategies. The first one is they use some special data augmentation. Normal data augmentation includes crop, rotation, flip, change of hue, saturation, exposure, etc. But for object detection, there are a set of data augmentation. For example, you can mix up 2 images. You can superimpose 1 images over another. You can just concatenate 4 images together to make the network harder to learn. Okay.
So it's called spatial. So why they call it
special?
Oh, special. Okay, special.
Yeah.
Okay.
The second type of tricks, they call it bag of special. They add some plugin modules or post-processing method. So here I think this trick is very interesting. It's called attention module. There are basically 2 types of attention module. The first type is channel-wise attention. Second type is point-wise attention. The intuition is that we need to pay unequal attention to different channels or different pixels. If we believe some channels are learning more informative patterns than the others, or some pixels, especially pixels in the middle, are far more important than the pixels at the boundary, then we can add some weights to different channels or different pixels.
So, but the point, maybe you can raise it later. Maybe you might be mentioned later, but would you please more specific about the channel? The channel means the channel in feature map?
Yeah, channel in feature map. Yeah. So, okay, so here you have a input feature map. Okay, then you have a side row here to learn a weight vector for each channel. Then you multiply that with the original feature map, so you get this colorful feature map. Okay, then some channels will get higher weights than the others. Yeah.
Okay, please go on.
And the second type, point-wise attention. So instead of learning a weight vector, here I learn a weight feature map. So it is multiplied back to the corresponding pixels in my original.
The point-wise is more like self-attention, right? If I'm correct.
Yeah.
Okay.
Okay. Then he also introduced the self-adversarial training. So it has two steps. The first one is to alter the original image such that the detector cannot predict the object correctly. Then second step is to, now I train a network to detect the modified image.
Yeah, one of the Yizhe's work is that Yizhe when apply a lot of the adversary samples, and we train the model with the adversary samples. So this is somehow like adversary training.
Yeah. Okay, so this is the performance for YOLO V4. There are two metrics we care when talking about the performance. The first one is average precision. It's basically the area under precision recall curve. The higher, the better. The second one is frame per second. Is specify the speed when we are making inference. You can see YOLO V4 is faster than efficient DAT, which is the previously best state-of-art network, compared to the last version of YOLO, which is YOLO V3.
So in this paper, they just provide intuition, but of course, all the intuitions make sense, but they do not, they're just saying apply these tricks and the YOLO model becomes much better. So may I ask, so I'm not sure, Yizhe, maybe Yizhe can know that where the position of the fast RCN here.
Yeah, there's no fast RCN.
Yeah, they do not compare with it. Okay, please go on. Oh, it's conclusion, right? Okay.
Okay, so there's 2 points I've talked about this before. I think this paper is more like a survey. The selling point mainly come from the extensive experiments they did. I think they have 4 pages to enumerate all the configurations they have.
Okay. Yeah. So how long does the paper?
How long? I forget.
Maybe
very long. Yeah.
Okay.
10 plus pages. I think the paper indeed offers a mature pipeline for one-stage detector. And okay, from my knowledge, it's hard to find a limitation in terms of the model design because they list a lot of tricks. And when I'm reading the paper, I have to search other papers so I can understand this YOLO V4. But the paper's contribution may not be significant as you mentioned, because it doesn't propose many new architectures or new laws. Just do some small modifications, then it magically boosts up the performance. Yeah. Okay, thank you.
Okay, I think Ruofan made a very excellent presentation here. It's more about object detection, a lot of tricks. Maybe these are tricks not only to improve the YOLO V4, but also for the two-stage model, right? So the self-attention, focusing on the attention, the channel attention, the pixel-wise attention, the spatial pyramid, the spatial pyramid poolings, and all these techniques can not only apply on the YOLO, but also apply on a faster RCN like two-stage model. Just like you can see, these tricks are not just applied on the YOLO, it can be applied on any. It's not specific for the one-stage model. It's also applied, it's applicable for a two-stage model. So I fully agree with Ruofan that this paper inventing or surveyed a lot of existing tricks to further improve upon existing YOLO models. Right. So is there anyone have questions? Yizhe or Zhangchen, do you have any questions for this presentation? I think it's very clear and we understood. Okay, if there's no other questions, let's call it a day. Okay, thanks again for Ruofan's presentation.